Hello everyone. So welcome back to our latest lecture session. So in the recent lecture sessions we have been discussing the applications with respect to the component balance and at the same time looking at how to use Vmintech to be able to understand the system and solve the system. So by this stage you should be conversant with pH, pKa, the deprotonated form, weak acid, strong acid, and how to use Vmintech to set up your particular system as in component balances, right. So now we are going to, today we are going to move on to looking at summarizing information, let us say, right. So for example you can always use Vmintech, but sometimes you want to look at a summary, let us say, you want to present the information to a layman, let us say, right. And for that particular case people in general out there in the field look at logC-pH diagrams, right. So on the y-axis you will have log C and on the x-axis you are going to have pH. So again why log C? Because pH is negative logarithm of H plus. To able to scale it, I guess, right, for scaling purposes we take log C on the y-axis and pH on the x-axis. And what is this, or what are these graphs in general typically used for? They are used for providing a snapshot of what your system is like or how your system is going to change with pH, right. So today we are going to discuss that initially. So let us look at an example graph here. So today we are going to look at logC-pH graphs, right. So again what are they used for? They are used for analysis. Again analysis. So earlier or in the recent past or even in the past, logC-pH graphs were primarily used when you had to make tedious calculations. But now with Excel, right, Microsoft Excel or any of those such mathematical tools or MATLAB and such, MATLAB is way too, it is a hammer in this case, I guess. So at least Excel and Vmintech, right, you can get your relevant information relatively easily. But in the past, let us say when we did not have the assistance of these computer tools, right, so you relied mostly on your logC-pH diagrams to be able to get an idea about the system, right. But people still use that in India considerably. So at least if you are looking at this course, hopefully the next time someone brings up a logC-pH diagram, hopefully you will be able to talk about Vmintech and such, right. Anyway, hopefully. So again let us look at logC-pH diagram. Keep in mind that this has been used in the past or has still or is still in use in India mostly though, right. So what else do we have here? Again we do the log C versus pH. Why? To be able to scale it. So what can we see? We can see the changes with pH. How does the system change with pH, right. So let us look at one example. I think the example that our example graph, I guess, that has obviously H plus and OH minus, and also I believe NH4 plus and NH3, and also the Stk acid, the protonated and the deprotonated form. So let us look at that graph here. So here let us try to take a few minutes to be able to understand our system. So here on the x axis we have pH and on the y axis we have log C, right, and log C, I guess C total depends on C total. In this case the particular graph is for a particular C. So again here the axis is from 0 to minus 14 and here 0 to 14, pH is from 0 to pH 14. So first let us try to analyze H plus and OH minus, I guess. So what are we looking at here? We are looking at H plus and we are also looking at OH minus initially, right. So again what is H plus? H plus is equal to minus log pardon me, not H plus, pH is equal to minus log concentration of H plus, right. So what happens as you increase the concentration of your H plus? The pH will decrease, right. As you increase H plus concentration, pH is going to decrease. As you decrease H plus concentration, the pH is going to increase, or similarly as you decrease the OH minus concentration, the pH is going to decrease. As you increase the OH minus concentration, the pH is going to increase, and more or less the same aspect mentioned over and over. So let us see how it changes. So we are going to look at H plus initially, and at pH 0 you see that log C the concentration is higher, and as you keep increasing the pH, right, what do you see here? You see that the concentration decreases, and here since we are looking at log C, that is why it is linear, right, we are looking at log C here, log C, this is what we are looking at, negative, that is why the slope is negative here. So pH log C versus pH. and so that is why you see a linear decrease here. So, from 0 to 14 here, right, that is what you see here, 10 power minus 14, pardon me, 0 to 10 power minus 14, and same case pH 0 to pH 14. So, at the same time, what would you expect? As H plus concentration decreases, it means the OH minus concentration increases, and that is what you see here. OH minus concentration is increasing from 10 power minus 14 to 10 power 0, right, and that is what you see here. Again, that is what you would expect here, right. So, we will look at how to, we will also try to look at a simple example, I guess, with monoprotic acid later on, and also look at H plus and OH minus, but we will come back to that later about how to go about that, right. So, for now we will still try to understand the logC-pH diagrams in a better manner. So, obviously, if you look at the point of intersection, that is going to be Kw value, and that should be 7, pH 7, right. And what does that mean? At that particular case, the concentrations of both H plus and OH minus are going to be the same, and we know that H2O dissociates into H plus and OH minus, and the dissociation constant is concentration of H plus into concentration of OH minus, right. So, that is 10 power minus 14, right, and when they are equal, they are both 10 power minus 7 and 10 power minus 7. So, that means at pH 7 anyway. So, that translates to pH 7. So, at pH 7 you see that both the concentrations are equal, and that is at 10 power minus 7. Again, you know, that is relatively easy to understand. So, let us move on to the next particular aspect. Let us look at Stk acid, something we have looked at until now, right. So, Stk acid, you know that the pKa is 4.7, right. We have a pKa of 4.7. So, now we are trying to look at Stk acid, the pKa is 4.7, right. And with your background, you know that when the pH is less than pKa, what does that mean? The deprotonated form is going to predominate, right, and when the pH is greater than pKa, you know that the protonated form is going to predominate. So, you know that earlier we looked at this speciation diagram where we looked at concentration versus pH, right, that is not normalized. So, obviously, this is what we looked at earlier, and this was HAC and AC minus, and this was pKa, right. And so, now obviously, if you are now taking the log C rather than concentration versus pH, you know, the shape is going to be relatively different. So, let me highlight the relevant particular graphs you are trying to look at. It is the red graph here, I believe, right. So, this is HAC and this is AC minus, right. So, again, let us try to understand the system here. So, here the pKa, you know, it is not going to be intersection of this point, but if you draw the slope here and also the slope here, the intersection of those slopes should be equal to your pKa, and that should be 4.7, or I think it is 4.76, right. So, the pKa of your particular system HAC and AC minus is going to be, or the pKa of that Stk acid is 4.76, that is what we just plotted here. And so, let us try to analyze the system now. So, when, or in this zone, right, when pH is less than pKa, what would you expect? You would expect that the deprotonated form is going to predominate. So, HAC is going to predominate. So, that is what you see. As you move from pH 0 to pH 3, almost all of it is going to stay as HAC, right, at least in the lower concentrations. So, as you keep increasing the concentration, though, there is slight increase, or you know, increase in AC minus. So, though it looks like there is a considerable increase, keep that this is just log C and negative here. So, the change is 10 power minus 3 or so on, which is relatively minimal, right. So, again HAC, most of it is in HAC, and so AC minus keeps increasing, and then at pKa, right, at around that pKa, you will have that particular concentrations to be equal, that is what you know, right. So, for a particular concentration, that pKa, the concentration of HAC at pKa, we know that the concentration of HAC will always be equal to the concentration of AC minus. pKa for your particular Stk acid is 4.76, and that is what you would see here. And again, as you move further out, as in this region now, right, what do we see here? We see that as we move away from the pKa, we said that most of it is now going to stay as the acetate ion or the deprotonated form, and there is going to be a rapid decrease in the concentration of your protonated form. This is your HAC, right, and this is your AC minus. So that is what you see here. Again, this will give me an easy idea about that, right, because this is logarithmic scale, right. Keep in mind that it means there is a 10 times difference in the concentration, right. It is a magnitude order of 1, right. So thus in general, let us say at pH 3 this is the concentration, and at pH 2 the AC minus concentration is here, and if it is off by unit of 1, that means it is off by it's 10 times lesser, and I can neglect that. So in this case, keep in mind that it is log C versus pH logarithm graph. So if one of your variable is less than by the other variable by unit of 1, that means you can more or less neglect it. 1 or 2 times change translates to 10 times or 100 times being lesser or greater. So you can accordingly neglect or use those particular values. So let us now move on to what we have here, or we will look at the other system here. So we are now going to look at ammonia here, NH3, okay, and hopefully I got that right, and NH4 plus, right. So that is what we have here, and now we are talking about NH3 and NH4 plus, and looks like the pKa is going to be around 9.1. let us approximate that as 9.1 from this graph. pKa is going to be the intersection of the slope, so it is going to be 9.1, let us say. I am assuming that as 9.1, that is a good enough assumption for now. So again, we are going to apply our basic knowledge as in pH less than pKa and look at how the system varies, and pH greater than pKa and look at how the system varies. So in this region, when the pH is less than pKa, what would you expect? Right, you would expect the protonated form to predominate. So let us look at that. So this is the NH4 plus, let me try to use a different highlighter probably. So this is your NH4 plus, and your particular NH3, where is that now, is out here, right, and the pKa value is 9.1. So what do you see here? So you see that in the range where the pH is below pKa value, what is going to predominate? It is going to be NH4 plus, and that is what you see here in this region. And as you are approaching the pKa value, which is here, right, what do you see? You see that it is going to be changing or shift in speciation from NH4 plus going to NH3. So this transformation you see in this zone, right, and as you keep moving further away from it, you see that now NH4 plus is going to decrease further, NH4 plus is going to decrease much further, and you are going to have an increase in your NH3, right. So again, we will look at a holistic view here. So thus more or less, or the logC-pH diagram will give you an idea about a summary, I guess. It is a snapshot of what you are looking for. So again, used in the past widely, but now with your computer tools such as Excel or your Vmintech, you can get this done easily. Again, with respect to Vmintech, one aspect is that all those data files that we were able to generate in our previous lecture sessions, you can easily output them or save them as in the Excel format, and once you save them in the Excel format, you can do the relevant what we say modifications or such in a presentable manner if you deem so, right. So let us look at how to we will look at one particular example here, right, and we will see, we will look at one particular example and we will see how we can go about analyzing it here. So what is the key here? We are going to express everything, right. Let me change the color to red. Okay, anyway, never mind. We are going to have to express all the concentrations as a function of H plus. This is what we are trying to do, right. You want to have everything because you are trying to draw a log C pH graph, right. So you want to express it in terms of H plus C. So more or less here you will have to make some assumptions, especially at the boundaries. So we are going to see what they are, I guess. So the first aspect is that we need to express everything as H plus, or you can, so that you can obtain concentration as constant, let us say, into function of H plus to the power of n or so on. So that is a usual form that you would look at, let us say. So let us look at one example. I think again we are going to look at the usual monoprotic example that I have been looking at. So let us say HA dissociates into H plus and A minus. So what are your species? Obviously they are HA, the deprotonated form is A minus, and obviously you will always have H plus and OH minus, right. So before we go further, we will just look at the simplest case, which is H plus. And how do we go about that? And we know that negative logarithm of H plus is pH. So what does that mean? It means log concentration of H plus is equal to minus pH. So that is one equation already, right. So you have log C versus pH. So that is equation 1. So that is obviously relatively similar, that is what you see here, I guess. What you see, as pH increases, you see that log C decreases, that is what we just looked at in the graph, right. As pH increases here, you see that log C keeps decreasing. Anyway, again OH minus, but for that we know that Kw is equal to H plus times the OH minus concentration. So the OH minus concentration is then going to be equal to Kw by H plus, right. And what is Kw? I guess the water dissociation constant, and you know again it is a constant similar to the equilibrium constant, and we know that the value is 10 power minus 14, right. And then let us move on again. So we take the logarithm on both the sides. So log of OH minus will be equal to the log of, what is this value here, Kw, minus the log of, what is it here, H plus, right. So log OH minus is going to be equal to log Kw, I guess I can write that as minus pKw, right, where pKw is equal to minus log of Kw, think of it as pKa, right, and plus pH, right. And what is this particular value going to be equal to? It is going to be equal to minus 14 plus pH. So this is my equation number 2. So what do I have here? I have log OH minus is equal to minus pKw, and pKw, and that value is going to be minus 14, minus pKw is minus 14 plus pH. Let us look at the graph now, and as you see, minus 14 starts from minus 14, right, minus 14 plus pH is our log OH minus concentration, right, or pH minus 14. So it starts from minus 14 when pH is 0, and as you see it keeps increasing until it reaches a maximum of 0. So that is what you see from this particular graph, right. So let us move on. I will move on to another fresh slide here. So next aspect is we need to be able to come up with approximating HA, concentration of HA, and what else please, also approximating concentration of A minus. So we are now into HA and A minus, the other two species, and so let us look at again what we are trying to do. So here let us say it is logC-pH graph, so you need to be able to look at some approximations. So we are going to divide that into two phases, and I guess the reference here is going to be pKa, right. So you are going to consider two cases, one the pH is less than pKa, and the other one the pH is going to be greater than pKa, and look at the relevant assumptions that you can make, and we are going to go through with that. So right, and in general we know that HA, the concentration of HA is equal to alpha naught into A total, and again what is A total? A total is equal to HA into A minus. Again the concentration of the protonated form we expressed as alpha naught, that is the first ionization fraction, right, into A total. Yes, and how did we define this ionization fraction? It gives us an idea about at least alpha naught. We define that as the protonated form, the fraction of the protonated form of the total acid, and that is what we have here. And so obviously this is not the product but the summation here, right, that is the total acid. So here let us say, and what do I know alpha naught is equal to? We know that alpha naught is equal to the concentration of H plus by H plus K, right. And what is K or Ka? Ka is the acid dissociation constant for the reaction Ha dissociating into H plus and A minus, right. So, that is what we have here. So, let us plug this in here. So, Ha is equal to alpha naught is H plus by H plus plus Ka into A total. So, now as we mentioned, we are going to look at two cases. What were they? When the pH is less than pKa, and the other one the pH is greater than pKa. So, we will consider the first case when H plus is far greater than K. What does that mean? So, H plus far greater than may is nothing but pH being less than pK, right. So, let us try to understand this system. So, the variable we are going to look at to simplify is going to be alpha naught. So, when H plus is far greater than K, right, what does alpha naught transform into? It transforms into 1 more or less. What does that mean now? So, when pH is less than pKa or far less than anyway, what does that mean? It means that almost all the particular acid is going to stay in its protonated form. That is what alpha naught equal to 1 means, right. So, again when pH is far less than pKa, what does that mean? It means that we know too from our background that all of your particular acid is going to stay in its protonated form, and so that is what you see here. So, at pH less than pK or when H plus is far greater than K, we see that and here I am writing that from here, Ha is going to be equal to A total, right, or log Ha is equal to log of your total acid, and that is my equation 3, right, and that is for one particular case. Where is that? When pH is less than pK, when pH is less than pK. So, let us try to look at our graph and see if that makes sense, and here I am going to look at HAC, let us say. So, pK is for 4.7. So, as you see, when pH is less than pKa, what do you see here? You see that it approximates saying that all the particular acid is going to stay as its protonated form. That is what you see here. So, let us move on, and now we will look at the other case. So, we are going to look at the other case when now H plus, right, is far lesser than Ka, or what does that mean? It means pH is greater than, I am just referring to this particular what do we say assumption that we looked at or case. So, it now means pH is greater than pKa, right. So, what does that transform into again? So, alpha naught again as we know is H plus by H plus plus Ka, right. So, because H plus is far lesser than Ka, I am going to approximate that as H plus by Ka, right. And so, where is my fundamental equation here? Ha, I am looking at this particular equation here. Ha is equal to alpha naught into A total, and that now is going to be equal to, substituting that here, H plus by Ka into A total, right. So, more or less let us look at what we have. A total is your particular total acid, that is more or less a constant for a particular scenario, right, and the denominator Ka, the acid dissociation constant for that particular acid, is obviously a constant, and so the only variable is your H plus. So, obviously log concentration of Ha is equal to log H plus log A total minus log Ka, and that is equal to log A total minus log Ka minus pH, right. So, again this is the case that would be applicable when pH is greater than pKa, right. So, that is what we just derived. So, we please keep in mind that we are making some assumptions here. So, what does that mean? When the pH is greater than pKa, as you keep increasing the pH, what happens to log Ha? It keeps decreasing. So, let us look at the graph here. Again, as we are increasing the pH, and we are talking about this zone now when pH is greater than pKa, as we are increasing the pH in this direction, we see that log HA is decreasing. So, that is what we just derived now. So, let us look at it now for the deprotonated form though, right. So, now until now we have looked at the protonated form. So, same case we are going to look at the deprotonated form. So, deprotonated form again, that is A minus concentration is equal to alpha 1 into A total, and again where is this from? We know that alpha 1 is defined that as concentration of A minus by concentration of HA plus concentration of A minus, that is equal to concentration of A minus by the total acid. So, that is where we have that from, and the first case again that we are going to consider is the pH being less than pKa. So, what does this particular alpha 1 transform into? We know that alpha 1 is equal to Ka by H plus plus Ka. So, when pH is less than pKa, so when pH is less than pKa, so the alpha 1 will be similar to pH less than pKa means H plus is far greater than Ka, right. So, I am going to say it is going to be equal to Ka by concentration of H plus, right. So, if I plug that particular value in, concentration of A minus is going to be equal to Ka by H plus, Ka by concentration of H plus into the total acid. So, now again what do we have the equation to be? We have A minus is equal to a function of H plus and other constants. So, that is what we want to have, right. So, let us write that down. Now taking the logarithm on both hands, on both the sides, log A minus or log C is equal to log Ka plus log A total minus log H plus. So, what does that mean? It means it is going to be equal to log Ka plus log total acid plus pH. Again, let us understand this equation please. So, we are looking at log C, and obviously as you see the deprotonated form concentration increases with pH, right. The deprotonated form increases with pH in which zone now? When pH is less than pKa, right. You see that is the case, and what do you see here? It is also dependent upon the total acid. What does that mean? So, the greater the concentration of your total acid, right, also the concentration of your particular protonated or deprotonated form in this case is going to be higher. So, again we looked at one particular case, and what was that? pH is less than pKa. Again let us try to understand this with respect to our graph. So, the log A minus should increase with pH, and let us see what we have here. So, in this particular zone with respect to acetic acid, if this is 4.76, when pH is less than pKa, right, we see that the deprotonated form Ac minus is now increasing with your particular pH, and that is what we just looked at in our particular graph, right. So, let us move on to the other scenario, and what is the other scenario please? The other scenario is for A minus is equal to alpha 1 into A total when the pH is greater than pKa, right. So, that is the other case we need to derive, and once we are done with that we will be done with this lecture session. So, again we know that alpha 1 is equal to Ka by what now? H plus concentration, H plus plus Ka, and when pH is greater than Ka, what does that mean? It means H plus is much lesser than Ka, right. So, if that is the case, alpha 1 will be equal to Ka by Ka, or meaning alpha 1 is going to be equal to 1. So, more or less A minus is going to be equal to A total. Again let us understand the system here. What does that mean? So, when the pH is greater than pKa, we know from our background too, I guess at this stage, that almost all of it is going to, it as in the total acid is going to stay as the deprotonated form, and that is what we see here, right. When the pH is greater than pKa, we can say that the deprotonated concentration, you know, of that species is going to be equal to the total acid concentration. So, again just taking the logarithm, it is going to be equal to log of A minus is going to be log of the total acid. So, that means it is a constant when pH is greater than pKa, and the constant is going to be equal to the log of the total concentration. Let us look at the graph again, okay, and in this region, as in when the pH is greater than pKa, what do we see here? We see that the deprotonated concentration, right, the deprotonated concentration of the deprotonated form, which is AC minus, is a constant, and what is the constant equal to? It is going to be equal to your log A total, right. So these are the log C-pH diagrams you usually come across, and you can understand them. So again, keep in mind that, let us say if I am going to try to compare two values, let us say, you know, I am going to compare at pH 7 the AC minus concentration and then the HAC concentration, right. This is what I am trying to compare, and I see that it's the both of them differ by unit of 2, but because it's log C, what can I say? I can say that, I can confidently say that I can neglect the HAC concentration and only the AC minus concentration is relevant. Why is that? Because it's a logarithmic scale, and you know, it's differing by unit of 2, right. So the order differs by 2, okay. So with that, I will be done for this lecture session, and thank you.